Here's problem 817. A spring, force constant 200 newtons per meter, is suspended with its upper end supported from a ceiling. With the spring hanging in equilibrium configuration, an object, mass 2 kilograms, attached to the lower end and released from rest. What is the speed of the object after it has fallen 4 centimeters? So we have a spring, and we put a mass, attach it to it, and we let go. The spring constant is 200 newtons per meter, and the mass is 2 kilograms. And we release it from this point, so let's call this situation A. And then after some time later, it has fallen to a lower position. It's fallen a distance x, and that is equal to 4 centimeters, so x is 0.04 meters. So not only has the spring compressed that, or extended that distance 0.04 meters, but also the mass has fallen that distance. And so we'll call this situation B. We'll say that our height at B is our zero height, so our height at A is 0.04 meters above that. Alright, so this is what we're looking at. Starting from the one equation, the rule them all, the kinetic energy at A plus potential energy at A plus any work done along the way equals kinetic energy at B plus the potential energy at B. By definition, we have defined the gravitational potential energy at B to be 0. However, we do have a spring potential energy, so at B we're going to extend that spring a distance x, so we'll have a 1/2 kx squared there. The potential energy at A is going to be mgh, where h is our height above point B. We're not going to have any spring potential energy at A because the spring is at its equilibrium position at that point. There's not going to be any work done along the way because we don't have any external forces other than gravity and spring, and we've already accounted for those by potential energy. So there's no work along the way. We're going to start from rest, so there's not going to be any kinetic energy associated at A, but we will have kinetic energy at point B. So this is what our equation looks like right now. We got rid of two terms, and then we just filled in the other terms. We want to solve this for the speed of the object at point B. So solving for the kinetic energy at B, that should be equal to mgh minus 1/2 kx squared. Multiplying both sides by 2 and dividing by m, taking the square root, we have the velocity at B is equal to 2 mgh minus kx squared divided by the mass, square root. So, putting in our numbers, we have 2 times the mass, which is 2, times 9.8, times the height, which is 0.04 meters, minus k, which is 200, times x, which is 0.04. The spring has been extended 0.04 meters. Square that over the mass, which is 2. All this square root. So if I do that, I got 2 times 9.8 times 0.04. That's 1.568 minus 200 times 0.04 squared, which is 0.32, all divided by 2, and all square root. I get 0.7899, I'd say 0.790 meters per second. That's the velocity at point B, and we found it by starting from our one equation to rule them all and evaluating the terms bit by bit. It's always nice to find the terms that are 0, get rid of those, and then find our other terms, mgh, 1/2 m velocity at B squared, and 1/2 kx squared. solving for the unknown, which in this case was the velocity of B.